We are going to solve a differential equation. Remember, a differential equation is an equation that is a derivative. So when we find the solution, we are finding the equation whose derivative is that. So the first example, example 1, says we're going to solve dy over dx is equal to xy. So the first step is always to separate your variables. First step, separate variables. Separate variables. So all everything with an x goes on the right side, everything with a y goes on the left side. So I'm going to divide both sides by y, and I'm going to multiply both sides by dx. So I get 1 over y equals x times dx. Now after I separate my variables, the next step is to take the antiderivative. In other words, we are going to integrate both sides, take the antiderivative. So the antiderivative of 1 over y is the ln of the absolute value of y, and the antiderivative of x is 1/2 x squared. And since they both are indefinite, I'm going to combine both of the constants and put it on the right side, because let's keep in mind that what we are doing is we are solving for y. So since I do not have an ordered pair, or what we call an initial condition, in order to solve for c, then we're just going to know that we have a constant in our answer. So the next thing, after you take the antiderivative of both sides, your job is to do whatever algebra you need to do in order to solve for y. So I'm going to raise both sides e to the something. E to the ln of y equals e to the 1/2 x squared plus c. Because I know that e to the ln of y is just y, I'm going to go ahead and drop the absolute value, since the argument will be positive anyway. And I'm going to rewrite e to the 1/2 x squared plus c. I'm going to make it e to the 1/2 x squared times e to the c. So let's take note that a to the x plus b is equal to a to the x times a to the b. Make a little algebra note there. Okay, and so since we do not have an ordered pair that we can plug in to solve for c, then we are pretty much finished because we've solved for y. So I'm going to write, I could leave it as e to the c, that's my constant, or I'm just going to call it a because we've got an exponential function here. Okay, let's look at the next example. So we're going to go to example 2. We're going to solve dy over dx is equal to 3y plus 6, given y of 0 is equal to 7. So in this situation, we do have an ordered pair. So we will be able to plug in the ordered pair and get what's called the particular solution to the differential equation. Okay, so I need to separate my variables first. First step is always to separate my variables. So I'm going to factor out this 3. Factor out this 3 so that I can multiply both sides by dx and divide both sides by y plus 2. So I do not separate variables by adding or subtracting. I only separate variables by multiplying or dividing. Okay, so now that I've separated my variables, I'm going to take the antiderivative of both sides, or make both sides an integral, so I can take the antiderivative of both sides. The antiderivative of 1 over y plus 2 is the ln of the absolute value of y plus 2 equals, and then the antiderivative of 3 is 3x, and remember the constant goes on the right side. Okay, so I separated my variables, and then I took the antiderivative of both sides. So now we have two things to do. We have to plug in the ordered pair to solve for c, and then we have to solve for y. So it doesn't really matter when you plug in the ordered pair, as long as you do it after you take the antiderivative of both sides. So I'm going to say e to the ln of y plus 2 is equal to e to the 3x plus c. So I know that e to the ln of y plus 2 is just y plus 2. And I have, remember what I did last time, e to the 3x times e to the c. So now I'm going to go to the right side, over to the right, and I'm going to plug in my ordered pair for y, 7 for y and 0 for x. So 7 plus 2 is equal to e to the 3 times 0 times e to the c. 7 plus 2 is 9. E to the 3 times 0 is just 1. So my constant, e to the c, is 9. So I'm solving for y, and I'm plugging in 9 for e to the c. So I have 9 e to the 3x, and I'm going to subtract 2 to solve for y. So since I had an ordered pair for this example, I could plug in the ordered pair and solve for the constant and get what's called the particular solution. When we don't have an ordered pair and we can't solve for c, then we get the general solution. Okay, let's do this one more time. Let's go to example 3, and we're going to do exactly the same thing. We're going to solve this differential equation given that y of 0 is equal to 0. So we do have an ordered pair, so we are going to be able to find the particular solution. So I'm going to multiply both sides by y plus 1, and I'm going to multiply both sides by dx to separate my variables. And then I'm going to take the antiderivative of both sides. I'm going to integrate both sides so I can take the antiderivative. The antiderivative of y plus 1 is 1 half y squared plus y equals, and the antiderivative of x is 1 half x squared plus c. Don't forget your plus c. Okay, so now I have two things to do. And now that I've found the antiderivative, I have to plug in the ordered pair to solve for c, and then I have to solve for y. So I'm going to plug in the ordered pair, 0, 0. 1 half 0 squared plus 0 equals 1 half times 0 squared plus c. So I see that the constant is 0. So that's good. Okay, so I got rid of that constant. I'm going to multiply both sides by 2 now, because I don't like working with that fraction, 1 half. So if I multiply everything by 2, I get y squared plus 2y equals x squared. Okay, so now I have to do some algebra in order to solve for y. So what I'm going to do is I'm going to do a little process we learned a long time ago called completing the square. So I'm going to do b divided by 2 and then square it so I can add 1 to both sides. Because if I do that, then y squared plus 2y plus 1 would be y plus 1 squared. And so now I can just take the square root to solve for y. So I get y plus 1 equals plus or minus the square root of x squared plus 1. And then I just subtract 1. So I get y equals negative 1 plus or minus the square root of x squared plus 1. But there's a big but here. We have to make sure that the solution has to go through the initial condition that we were given, which is y of 0 equals 0. So we have to plug in 0 for x and 0 for y to see whether it's the plus or the minus. So let's see. We get 0 equals negative 1 plus the square root of 0 squared plus 1. Is that true? Or is 0 equals negative 1 minus the square root of 0 squared plus 1? Which one of these is true? Well, negative 1 plus 1 is equal to 0. Negative 1 minus 1 is not equal to 0. So it is only negative 1 plus the square root of x squared plus 1. And there's my solution.